Assalamualaikum and hi everyone. Today, our group AS1205_1 will be presenting on gas chromatography, an efficient analytical technique that separates and analyzes chemical compounds. This presentation was prepared for Madam Munirah binti On. Before we begin, let me introduce our group members. Here are the members of our group. The first one is Nur Aliyah BATRISYIA binti AHMAD SHABIDIN, FATIHAH NABILA binti Muhammad SHAHRAN, followed by SITI BALQIES binti Muhammad YUNUS, and myself, Muhammad Amir Asyraf bin Muhammad ZUHDIN. Last but not least, Muhammad DANIAL bin SUHAIMI. Now, we will proceed to the introduction of gas chromatography. Before we dive into the details, let me briefly explain what gas chromatography or GC is. GC is a highly effective analytical technique used to separate, detect, and quantify volatile and semi-volatile compounds in complex mixtures. In a GC analysis, the sample is vaporized and carried through a thin column by an inert carrier gas, usually helium or nitrogen. Inside the column, different compounds interact differently with the stationary phase, which causes them to move at different rates and elute at different times. These separated compounds are then measured at the end of the column, producing a chromatogram, a graph where each peak corresponds to a different compound. Because of its high sensitivity and precise separation, GC is widely used in environmental analysis, pharmaceuticals, forensic science, and quality control. Now that we understand what GC is and why it is important, let's move on to the background of the technique. Before we discuss the objectives of our experiment, let's look at some background on gas chromatography or GC. GC is a powerful analytical tool used to separate, identify and quantify volatile and semi-volatile compounds. In this technique, the sample is carried through a column by an inert gas, usually helium or nitrogen, and the column is paired with a stationary liquid phase. Components of the sample separate because they move at different speeds and are detected as peaks in a chromatogram. GC is widely used in environmental analysis, pharmaceuticals, forensic science, and many other fields because of its high sensitivity and reproducibility. Modern instruments are even more advanced, often using detectors such as flame ionization detectors (FID) or mass spectrometers (MS) for enhanced precision. Its ability to analyze complex mixtures in just a few minutes made GC an essential tool in research, industry, and quality control laboratories. With this understanding, we can now move on to the objective of our experiment. Before we start the experiment, it's important to know what we aim to achieve. Our objectives were as follows. First, to determine the retention times of N-butanol and 2-propanol. Next, to identify the components in a standard mixture based on their retention times. Then, to identify the component present in an unknown sample. Finally, to study the effect of temperature on retention time and resolution. Now that we know our objectives, let's take a look at the instruments used in gas chromatography.
This slide shows the block diagram of a gas chromatograph which explains the flow of the system from start to finish. First, the process begins with the carrier gas. The carrier gas enters the system and flow into the flow controller, where the gas flow is regulated before moving forward. Next, the carrier gas passes into the injector. At this point, the sample is introduced into the system and joins the carrier gas stream. After injection, the sample is carried into the column, which is placed inside the oven. The column remains in the oven as the sample moves through it. Once the component exits the column, they flow directly into the detector. The detector receives the separated component one by one. The signal from detector is then sent to the computer for processing. Finally, the result is displayed as a chromatogram on the computer screen, showing the output of the analysis. This is the function of instrument for gas chromatography. The first one is carrier gas, mobile phase that transport the sample through column for separation. Common carrier gas are helium, nitrogen, and hydrogen. The second one is a flow controller. Control the flow rate and pressure of the carrier gas into the GC system. Stable and accurate flow is critical because even a small variation can affect separation efficiency, retention time, and peak shape. The third one is injector. Introduce the sample into the GC. The injector is heated for ensuring sharp starting points for separation. Next, column. Separating mixtures component based on different interaction with stationary phase, while oven provide precise temperature control of the separation column. Temperature influence the interaction of compound with the stationary phase. Other than that, detector detect compound as they elute from the column and convert their physical or chemical interaction into electrical signal. The detector's output is correlated to amount of analyte present. Next, amplifier increase the electrical signal produced by detector before it recorded by the data system. And the last one is a chromatograph, which a visual output of the GC, typically a graph plotting detector response versus time. Each peak corresponds a different compound elute from the column.
Now I will explain about the sample handling. In this experiment, the chemical used were true propanol and butanol and standard mixture of true propanol and butanol in 1:1 ratio, also the unknown sample. First, the syringe is rinsed with the distilled water before filling it with the sample. The volume of the sample taken may be more than the required volume. Care must be taken to ensure that no air bubble present in the syringe. If air bubble are observed, the syringe is gently tapered to remove them. Next, the syringe is held vertically with the needle facing upward. The plugger is pushed slowly until the required volume is obtained at eye level. Any excess sample is removed using a tissue. Since the sample used are volatile, the preparation and injection of the sample must be carried out quick as possible. Now I will talk about the experimental. First, the gas chromatography instrument is switched on and the operation conditions are set. Oven temperature is maintained at 70 degrees Celsius while the injector and detector temperature are set 180 degrees Celsius. Next, the individual components are injected separately to determine their retention time. After that, a standard mixture is injected and the components are identified by comparing their retention time. Then the unknown sample is injected and analyzed using the same retention time by comparison method. The column temperature is subsequently set to 100 degrees Celsius to observe the effect of the lower temperature of retention time and resolution. Finally, the oven temperature is increased to 140 degrees Celsius to study the effect of high temperature on separation of the component. Now it's about the operation of gas chromatography. This illustration shows the operation of gas chromatography that used in this experiment. For manual injection, the sample is injected into the septum liner before switching on the instrument. The oven column is checked to ensure that the instrument is in the off mode. The instrument is switched on. If the gas supply is insufficient, a warning tone will be sound. On the computer, instrument 1 online is selected to allow the instrument to complete its setup. After the setup completed, method is selected, followed by edit entire method and all parameters are checked. For small sample quantity, simplest mode is selected. While simplest mode is used for high concentration sample, constant pressure mode is chosen. Column number 2 is selected with the inlet set to back and the outlet set to ambient. The flame ionization detector FID is used. The injection parameter are set to 5 minutes with a volume of 1 microliter. The method is applied and saved. The operator name and sample name are entered and the run method is selected. The sample is injected quickly and the start button is pressed immediately. The data obtained and then analyzed.
This is the attachment of standard mixture at 17 degrees Celsius, 2 propanol and butanol. This is an attachment of unknown sample, standard mixture at 100 degrees Celsius and standard mixture at 140 degrees Celsius. The result is based on the attachments. At 70 degrees Celsius, the standard mixture shows 2 rotation times at 2.676 and 5.830 minutes. Individually, true propanol had a rotation time of 2.709 minutes while N-butanol showed 5.973 minutes. The unknown sample recorded a rotation time of 5.971 minutes, which closely matches N-butanol. Therefore, the unknown compound is identified as N-butanol. When the temperature was decreased to 100 degrees Celsius and 140 degrees Celsius, the retention times decreased to 2.271 and 3.278 minutes and then to 1.956 and 2.236 minutes respectively. The interpretation of the result. The standard mixture produced 2 peaks corresponding to 2 propanol and N-butanol. The unknown sample showed a retention time of 5.971 minutes, which closely matches the retention time of N-butanol, 5.973 minutes. Therefore, the unknown compound was identified as N-butanol. An increase in temperature resulted in a decrease in the retention time of the standard mixture solution.
Now, moving into the discussion of our result. First, For identification of the analytes, we identify by comparing retention time of standard mixture with another analyte's retention time. We detect that peak 1 of standard mixture, eluting at 2.68 minutes, confirmed as 2-propanol, and peak 3 of standard mixture, eluting at 5.83 minutes, confirmed as N-butanol. This elution order is intertwined to their boiling point, meaning that N-butanol has high boiling point compared to 2-propanol. But in contrast, the 2-propanol was more volatile and entered the mobile phase faster than N-butanol. Also, by matching these two analytes with unknown sample, we confirm that the unknown sample was matched N-butanol at 5.97 minutes. For the effect of temperature on retention time, when we look at the effect of temperature across 70, 100, 140 degrees Celsius run, we saw a distinct pattern. As the temperature of the oven rise, the retention time was decreased. For example, N-butanol dropped from 5.83 minutes in 70 Celsius to 2.24 minutes in 140 Celsius. It seems that its retention time was cut by half. This happened because higher heat increased the analyte vapor pressure, reducing the interaction with the stationary phase. However, there is a trade-off regarding impact on the effect of temperature on peak resolution. While 140 Celsius was the fastest run, the gap between the two peaks decreased significantly. Thus, we observed that low temperature provide better selectivity, but it also caused a peak broadening due to longitudinal diffusion. Therefore, we decide that 100 Celsius provide the best balance of sharp peaks and baseline separation. Finally, regarding our laboratory operations, safety precautions were our very top priority. When in operation, we ensure that the injector and FID zones were allowed to cool before performing any maintenance or column change, as these zones significantly higher in temperature than oven. The system remained in not ready state until the injector and FID zone are stabilized. Thermal equilibrium is essential for reproducible result. For ensure the accuracy of the result, we make sure that the temperature was set to the desired temperature, all the sample in the right order, and sample information were entered correctly. To conclude our presentation, we have successfully met all the 4 objectives by gas chromatography analysis. On the first objective, we successfully determined retention time decreased as temperature increased for N-butanol and 2-propanol. Also, for the second objective, we correctly identify the standard mixture contain both N-butanol and 2-propanol based on the retention time. Regarding the third objective, we also identify the unknown contain both alcohol via retention time matching. For the final objective, we confirm that increasing temperature reduce retention time speed but decrease resolution, separation quality. In summary, we found that the 100 degrees Celsius temperature provide the ideal speed and separation quality while maintaining safety precautions for high pressure and high thermal instrument.